Okay, so in section 5.1, we talked about the end behavior of a graph as well as what happens at the intercepts. So in this section 5.5, we're going to focus a little bit more on those zeros of the polynomial, and then we'll end this unit with section 5.6, which is going to talk about the imaginary zeros. So we'll do some recap of imaginary numbers for the next section. But one of the things that you'll find between what we did in that R6 section with synthetic division is that it was a nice way to show how to find a remainder, a quotient, and all those things. What might be sort of a little more efficient is another way to find that remainder. So yes, you can certainly do synthetic division, but in some cases it might be easier to do it another way, and that's what leads us to the remainder theorem. Okay, so the remainder theorem is sort of a follow-up with what we do with synthetic division. As you know, with synthetic division, we can take some polynomial function, f of x, and divide it by x minus c. Well, it turns out that the powers that have proven this years and years ago, that the remainder can also be found another way. And that's simply by taking that function and replacing it with c. So whatever the root is, so if you have x minus c, the root is some number c, that means you can simply substitute the root into the function to get the remainder. So I'll show you the idea of what we've been doing with synthetic division and this hopefully more efficient way of doing it. So in this first example, we have some polynomial that's may or may not be easy to factor, but we want to see what the remainder is when we divide by x minus 1. So of course, that means our root is 1 that we're trying to test. All right, so we put 1 in our little side there. Our coefficients are 2, -3, and 4. And then simple synthetic division should get us a remainder fairly quickly. Bring down the 2. 2 times 1 is 2. Add -1. -1 times 1. And our remainder is 3, right? So that's very straightforward, and we did that in that last section. Well, according to the remainder theorem, you can take that root 1 and plug it in to your calculator. So simply, and I'm going to show all the work, 2 times 1 squared minus 3 times 1 plus 4. If you just substitute that in, you will get 2 minus 3 plus 4, which, lo and behold, equals 3. So is synthetic division easier? Is substituting the root itself easier? It kind of depends, I suppose, on the function and how crazy it looks. But those are two different methods of finding a remainder. And of course, the whole point of finding a remainder is to determine if something is a factor. And so we talked about this with the synthetic division last time. Here we're just formalizing it. If you plug in some root c and it equals 0, then that tells you that the factor x minus c exists, okay? Similarly, if you have x minus c and you know it's a factor, then you know that when you plug in the root, you're going to get 0. So it works both ways, okay? So these next examples are very quick, and it just sort of reinforces this idea. So here's another polynomial, 2 parts. First, find the remainder with that x minus 3. Now you could do synthetic division, of course, but we're trying to apply the theorems to it. So we're going to take 3 and plug that in, right? So f of 3, and again, I'll write this out just so you can follow along, but really you can just type this in on your calculator and have no problem, right? Of course, we're just substituting all the x values with 3, pretty straightforward. And I'll write everything out just so that we're not making any mistakes. 3 cubed is 27, times 2 is 54. 9 times 5, 45, plus 3 minus 6 equals 6, right? If you synthetically divided, you would also get a remainder of 6. Now all we're doing is applying the factor theorem to determine is x minus 3 a factor of the function. Well, obviously, since f of 3 does not equal 0, right? F of 3 does not equal 0, so therefore x minus 3 is not a factor. That's pretty straightforward. That's all it is, right? So at the end of the day, you're substituting a value for x into deciding whether it equals 0 or not, and then determining a factor. Some pretty straightforward stuff. We're just formalizing it. And those of you who go on to upper level mathematics, you can certainly find out why these theorems are true and prove them. But for most of us, just suffice it to say that, okay, that's a fun little trick, and we can move on. One final thing before we get into sort of a little bit more involved part of this is a quick idea about the maximum possible zeros. We talked in an earlier section about turning points and how turning points had a maximum of 1 less than the degree. Well, in this case, when we're talking about actual zeros, and we're talking about real and imaginary, right? So any kind of zeros you have, some are real, some are imaginary, maybe they're all one or the other. The maximum number of zeros that a function can have is equal to the degree. Pretty straightforward idea. So in this last example, what is the maximum number of zeros that can exist for this polynomial? Well, the degree is 5, right? So since the degree is 5, there are a maximum of 5 possible zeros, of 5 real and imaginary zeros. And we'll talk about the imaginary ones next class. But that's the idea of that application. So some pretty straightforward concepts, I think. Certainly not a ton of math involved, which I think is always a welcome addition. So just some things to keep in mind, and hopefully the homework problems should go pretty quickly. The biggest theorem that we'll talk about today is what's called the rational zeros theorem. So you have a calculator which will sort of expedite the process here, but we want to kind of give you a little background into how this comes along. And so here's the idea of the rational zeros theorem. So you have a polynomial, right? So the first thing you have to have is some polynomial, fine, and it's going to be equal to 0. So it's set it equal to 0 as if you're trying to factor it. All right, so the idea here is that the coefficients of the polynomial, and here's sort of a big caveat, the coefficients of the polynomial all must be integers, right? So no fractions would be your coefficients. And most of the time we don't see fractions anyway. So when we have a polynomial that have integer coefficients, we can kind of investigate this theorem. What this theorem says is that there is a ratio of two numbers, and we call it P over Q. So if you take P and divide them by Q, you're kind of leading into what we're doing with this theorem. What is P? Well, a P is a list of all of the factors of the constant. So whatever the polynomial is, you want to look at the constant, and that's going to be a list of their factors is going to be P. Then Q is a list of all the factors of the leading coefficient. So we're basically looking at the last term and the first term. And it's sort of like, and this is sort of a loose translation, but if you're familiar with the X method, when you use that to factor binomials or longer functions, it's sort of where you take the first term and the last term and do some multiplication. This is sort of a variation on that. So you're looking at the factors of the constant and the factors of a leading coefficient. And when you take a list of every combination of P divided by Q, it could be, we say could be, it's a potential zero of the polynomial. So what you'll be asked to do, at least to start, is just to list the potential zeros. Now there's going to be far fewer than them, right? So like if you look at this first example, the leading term is 2x cubed. So that means there's going to be at most 3 real zeros, right? We just kind of talked about that. But to give you an idea of what the zeros are, you can list all of the P's and the Q's, all right? So again, the P's are the factors of the constant, and so the constant is -4. Well, what are those factors? You have plus or minus 1, plus or minus 2, plus or minus 4, right? These are all your factors of -4, right? So kind of think back to middle school math when you were listing the factors of a number. Q are all the factors of the leading coefficient, which is 2. Well, it's obviously 1 and 2, right? 2 is a prime number. But you could have -2 and +2, so don't forget the plus or minus. So these are all your factors of the constant and all the factors of the leading coefficient. And what you have to do is take each of the factors of the constant and divide them by each of the factors of the leading term. So if you take 1 divided by 1, you get 1. You take 2 divided by 1, you get 2. You take 4 divided by 1, you get 4, and then go with the second one. 1 divided by 2 is 1/2. 2 divided by 2 is 1, we've already reduced that. 4 divided by 2 is 2, we've already reduced that. So what we have here are your list of all potential zeros. So there are 8 factors here, right? There's only 3 that can be zeros. So we have to figure out which of these 8 would be factors. Now there's a little bit easier way to do it. The old method says to take, to do synthetic division and pick one and hope that you're right. We'll kind of do it a little bit more structurally, but that's the idea. So on the homework, on even the test, we'll give you a multiple choice question or two that asks you to find all the potential rational zeros. And so that's the process you want to do. All right. So in the second example, you can sort of pause the video and see if you can find the P's and Q's on your own. And then when you come back to the video, you can see if you're right. So if you come back to the video, the factors of 9 are your P. So that's plus or minus 1, plus or minus 3, plus or minus 9. Okay, fine, no problem. And then you can take all their factors of the leading term. So 6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, all right? So those are your factors. And of course, we take each of the numbers in P and divide them by each of the numbers in Q. And you can see it's sort of a process. So I take every number in P divided by every number in Q. 1 divided by 1, 1 divided by, let's do 3 divided by 1. We'll go from all the P's divided by all the Q's. And then 9 divided by 1. All right, so I've taken all the P's divided by the first Q. Now take all the P's and divide it by the second Q. 1 over 1 we did. 1 over 2, 3 over 2, and 9 over 2. All right, so we took all the values of the 3 and divided them by each of the factors there. Okay. And then we'll do the 9, and we did divide each of them there, and we have our list. So we've got 9 divided, see, what was I doing here? Okay, there we go. 1 divided by 3. 1 divided by 6. We haven't done that one yet. Then we have 3 divided by 1, 3 divided by 2, 3 divided by 3 is 1, 3 divided by 6 is 1/2. And finally, 9 divided by 1, 9 divided by 2, 9 divided by 3 is 3. We reduced that, and 9 divided by 6 is reduced to 3/2. So we have all of them accounted for. And so as long as you've listed all of your factors, you've got them listed. So obviously there's going to be a ton of repeats. And so just be careful that you don't duplicate them, but it's no big deal if you do. But whatever process works, if you want to take each P divided by each Q, or do it 1 P at a time, whatever works for you, and just make sure that you can get all of the factors. And so it's sort of a long process, right? It's not exactly the quickest thing. And so the idea, again, is that of these 1, 2, 3, 4, 5, 6, 7, 8, 16 quotients, right? P divided by Q. Of these 16 options, we only want 3 to be the actual roots. And so we have to figure out which 3 they are. What you can figure out pretty quickly is that the bigger the numbers are for the constant and the leading coefficient, the more factors they are, and the more combinations you can have in your list. So when you get these with really big coefficients and constants like 12 and 24 and 18 and 20, you get a lot of factors. So we're going to kind of keep it simple and keep it with numbers that have, just a handful of factors, so you can not go too crazy trying to list them all. All right, so what's the point of this? So the point is, once you list the potential rational zeros, you can actually find them and then factor the function. So we're going to be able to factor higher level polynomials. So in this first example, we have a 4th degree polynomial. That's not exactly easy to factor, right? You're used to quadratics, pretty straightforward. But anytime you get above a quadratic, unless it's a special case like a difference or sum of cubes or a difference of sum of like squares that happen to be a fourth degree, there aren't really a lot of ways to factor. So by using the rational zeros theorem and synthetic division, we can factor any polynomial. The key is to try to keep using the synthetic division over and over again, so you can repeat the synthetic division until you're left with a quadratic. Because we know how to factor quadratics, right? So when you get a quadratic left over, then you can use any number of ways to solve quadratics, okay? All right, so let's take a look at this. According to the process of the rational zeros theorem, what you want to do is list all the possible roots of the constant. So we have plus or minus 1, 2, 3, 4, 6, and 12, right? Those are all the factors of negative 12. We kept it simple for q. There's only one factor of 1, right? So the possible roots are simply p divided by q, which is just a repeat of p, right? So these 12 factors give you a pretty comprehensive list of what might be the roots. Now, before calculators, they would want you to guess. Pick one, synthetically divide, and see if it works. Well, we luckily have the joy of having our calculator, right? So we can go to our calculator and we can clear it out and we can look at the function. So let's type in our function, x to the fourth plus 2x cubed minus 7x squared minus 20x minus 12. Okay, so we're going to graph that, and we can kind of zoom in a little bit if we want, and we can see a couple things going on, right? So we can look at this. Now, graphically, we can figure out all three of the 4 zeros, which is kind of nice. And you maybe know by multiplicity that we actually have all the factors. So I'm going to take factors that go through the graph. And so this graph is pretty straightforward. And if you zoom in, or you can use your plots on your calculator. Remember, on your calculator, you can always go to second trace and do a calculate 0 option, right? So you can go to second trace 2 on your calculator. And that will give you the 0 option. And you can play with your calculator to get the intercepts. Or you can look at your table. Right? You can always look at the table as well. So what we're going to do is basically prove that these are the zeros using synthetic division. So I'm going to take the one on the right, which is 3, and start there. Okay? So I'm going to take my 3 and synthetically divide my polynomial. 1, 2, negative 7, negative 20, and negative 12. Okay, if I synthetically divide, 1 times 3 is 3, add 5, 15, 8 times 3 is 24, that's going to be 4 times 3 is 12. Now, it shouldn't surprise you that the remainder is 0, right? We knew it crossed the x-axis, so it better be a 0, right? It's a factor. We know this because it crosses the x-axis. So we know that x minus 3 is a factor. Okay. We also, by virtue of looking at our graph, know that negative 1 is going to also cross the axis. And so negative 1, again, these are in our list, so that works out well. I can take my values that I have in my quotient and do synthetic division a second time with those new numbers. And then bring it down. 1 times negative 1, we have 4. Negative 4 is 4. Another negative 4 is 0. Again, it shouldn't surprise us that we have a 0 for a remainder. So our factor here is x plus 1. Now, we know because we looked at the calculator that negative 2 is our other 0. But let's say we weren't so obvious. We didn't know that. What we could do is take what we have left in our quotient and factor that, because what's left is a quadratic. How do I know that? Well, I started with x to the fourth. When I divided synthetically by 3, I was left with x to the third. When I divided synthetically again by -1, I was left with x squared plus 4x plus 4. That will be a quadratic that you can most likely factor. And factoring this out gives you x plus 2, x plus 2, which we like to call x plus 2 squared. And that shouldn't surprise you because -2 is where it touches the graph. It's got an even multiplicity, so it shouldn't surprise you, it shouldn't surprise you that our factor is x plus 2 squared. If you add the x plus 1 and the x minus 3 from before, we have our final answer, and this is the 4th degree polynomial in factored form. Okay, so that's the process. The numbers were pretty straightforward, so we wanted to demonstrate it to you on a calculator so you could see it. You're not always going to have nice, easy numbers. And so the next 2 examples just get a little bit more difficult with the results. It's the same process, but I'm going to show you some of the little nuances that happen when you have some things that go not so according to plan. And then once we get through these 2 examples, the last part is very quick. So we want you to go through the process of finding the P's and the Q's just so we know that all of these are possible options, right? All of the factors in the last example were in our list, right? These were part of the options that we had. So if we take our factors of 2, plus or minus 1, plus or minus 2. Factors of Q, also, plus or minus 1, plus or minus 2. So your possible roots, take the P divided by Q, 1 over 1, 1 over 2, 2 over 1, and 2 over 2. Okay, so these are our possible roots, and notice we could have a fraction. Okay, so let's pick one, let's go on our graph. So in the interest of time, I'm not going to graph it on the calculator, but if you graph this function, it shows that the graph crosses the axis at x equals 1, right? So that's going to be a root because our graph will tell us this. So we're going to show that synthetically. Right? We have our 1, we've got our synthetic division, and then we're going to simplify. Bring down the 2, 2 times 1, add them, 1 times 1, add them, -4, add it, -2, 0. Okay, again, not surprising, it's 0. Then we look at our graph again, and our graph shows that -1/2 is a 0. So if you look at your graph, it would be between 0, -1. And so you could either use your second trace option, or you can just kind of guess. But you know that if it's a fraction, it's got to be 1/2. And it's on the left side of the y-axis, so it's got to be -1/2. Okay, so we're going to take that -1/2 and use our results from the last quotient, 2, 1, -4, -2. And we have, bring down the 2. 2 times -1/2, ooh, that's tricky. That's a -1. Add it, 0, 0 times 1/2. -4 times -1/2 is 2. And again, you're going to have a remainder of 0. We are left now with a quadratic. That was the goal, right? We went from a 4th degree polynomial, we divided twice, and so we have a 2nd degree polynomial. We're left with 2x squared minus 4, and we want to factor that. Well, factor out of 2, we have x squared minus 2. Now, you can't really factor that nicely, but we know that if you take x squared minus 2 and solve it, x squared equals 2, x equals plus or minus root 2. And those are your factors. X minus root 2, x plus root 2. Okay? So if we take the factors that we got graphically, x equals 1, x equals -1/2, and then the 2 factors we just figured out here, we can combine it all into our final answer of 2. Doesn't really matter the order, but I'll go x minus 1, x plus a half, x minus root 2, and x plus root 2. So we just factored a 4th degree polynomial using synthetic division. This would be impossible to do any other way because 2 of our roots are irrational numbers. The square root of 2 and negative square root of 2 we wouldn't get by conventional factoring techniques. So synthetic division allows us that idea. Right, when you graph this, you probably saw that there were 2 times it crossed that didn't actually make it a nice easy number. So when you have some weird numbers that aren't nice, fractions or decimals, you know that there's going to be other roots. So this gives you all the rational roots, right? It's called the rational root theorem, but there could be irrational roots such as that. So there are some things that, it's limited in its capabilities, but it gets you to a point where you can factor a quadratic, and that's our goal. All right, so one final one just to drive this home, and then we can move on. Okay, so we have our p's, which are our factors of 2, plus our 1 and 2, and then factors of 3, plus or minus 1, plus or minus 3. What are your possible roots? P divided by q, 1 over 1, 1 over 3, 2 over 1, 2 over 3. Okay, so these are your rational roots, things that can be written as a fraction. There may be irrational roots, who knows? But this gives you at least an option of all of our rational ones. Let's graph. When you graph, it shows that x equals negative 1 is where the graph crosses, all right? Okay, so that means we can do synthetic division at negative 1. 3, 4, 7, 8, 2. So synthetic division, 3, negative 1 is negative 3. We have 1, negative 1, 6. Negative 6 is 2. Negative 2 is 0. No surprise there. Then it gets a little tricky because the graph crosses not at a nice whole number anymore, but it only crosses one other place. So if you use your second calc, if you use any other tracing function, you can find that x equals negative 1/3 is the second root. And getting that one is a little bit trickier, but if you understand the calculator process, you'll be okay. I wish I could do it on my calculator here because it doesn't have that option, but again, it's under second calculate, second trace, go to 0, and you can get that root. All right, so negative 1/3 on the calculator, I'm sure it shows as negative 0.33333, so convert that to a fraction and synthetically divide. So negative 1/3 with our quotient, 3,162. Hopefully you've realized that 1 negative 1/2 was an option here with a leading term of 2. Negative 1/3 is an option here with a leading term of 3. So it cancels out very nicely. 3 times negative 1/3 is negative 1. 0 times 1, 6, negative 2. The numbers work out very nicely, right? And so you're left with a quadratic. So we have 3x squared plus 6 equals 0. You can factor that, 3x squared plus 2. Now notice, in the last example, it was x squared minus 2, which had a solution. If you take x squared plus 2 and solve it, it has an imaginary solution. So we're not going to use imaginary numbers, so we're not going to have any real scenario here. So we're going to keep this kind of a prime factor as it is, and we're just going to add the other factors that our calculator showed us, right? So we have our 3x squared plus 2 factor. We're going to leave that as an unfactored quadratic because it's not factorable. It has no real solutions. And then we're going to write our other roots, x plus 1 and x plus 1/3. Okay? And so that is your factored version of this 4th degree polynomial. Okay? So a couple little things to keep in mind. It's nice in example A when all the rational roots were whole numbers, it all worked out nicely, the graph showed us everything. That's not always the case. when you have fractional answers, you know that you're going to have some potentially interesting answers. And so in this case, we had a fractional root, and we also had an irrational root. We had negative and positive square root of 2. So that could happen, right? You just got to use your factoring or solving skills once you get it to a quadratic. And that's really the key of this, is getting this down to a quadratic function so you can simplify it as much as possible. Okay, if you have any questions about the calculator, please let me know in class. Just make sure you can get the calculator roots, because the last couple examples really ask you to do that. Okay, so in this last example, we wanted you to factor. And so because we asked you to factor, there's a lot of process that went through this, right? When we ask you to solve, this is a much easier scenario. You don't have to do any synthetic division. You don't have to do any factoring. You just use your calculator, right? So I don't even give you a lot of space, because I want you to use your calculator when they ask you to solve, right? If you want to go through and synthetically divide, go for it, right? You'll find some numbers that are pretty straightforward. And so these will give you sort of a nice scenario. And I'll just type this in here. We have x to the 5th minus 5x to the 4th plus 12x cubed, right? These are pretty crazy polynomials. 24x squared plus 32x minus 16. And so when we graph this, we can see, oh, we have it crossing the axis at 1 and touching the axis at 2. And so that's an even multiplicity and an odd multiplicity. And that makes sense because we have a 5 degree, right? A 5th degree polynomial. And so we could factor this if we wanted to. It didn't ask us to, so I'm not going to. I'm just going to know that my solutions are 1 and 2. Have a nice day. That's all you have to do. X equals 1 and x equals 2. Done. Okay? Even if you wanted to synthetically divide, you couldn't necessarily do it here because we don't have an integer coefficient. And so you're just going to, again, use your calculator. And when you graph it, you'll see that it crosses in between 1 and 2. Right? It only crosses once because you have some imaginary zeros, which we'll talk about again next time. Okay, our final thing here is that we want to talk about what's called the intermediate value theorem. This is a pretty straightforward theorem. The wording is a little bit crazy, but if you think about what's being asked, and I'll explain it, they'll be like, oh, that's all they're asking? Pretty straightforward. So what this says is if you have two numbers, one of which is less than the other, 2 and 3, 5 and 10, whatever, if you plug them into your function, whatever that polynomial is, and if they have opposite signs, one is positive, one is negative, then there is some zero between them, right? So graphically, all we're saying is if you have some polynomial and you pick two numbers, we'll call this A and we'll call this B. If one of them has a value that's positive and one of them has a value that's negative, since it's a continuous function, there has to be some number that equals 0. That's all we're saying. It's just saying if you're connecting 2 points, at some point it's going to cross the x-axis. That's all the intermediate value theorem says. Okay? So we're just going to use that theorem to show that a polynomial has a 0. So here's our polynomial, and here are the a and the b values, right? All you've got to do is plug them in and hope that they have opposite signs. So when you plug in 1 to the 5th minus 1 cubed minus 1 is negative 1. Plug in 2 to the 5th minus 2 cubed minus 1. Plug that in, it's positive. Wow, look at that. 0 is between negative 1 and 23. So there exists a 0 between 1 and 2. What is it? I don't know. I don't care. It didn't ask, but there is a 0 between 1 and 2. All right? So if you were to graph this and look, you'll see it crossing somewhere between 1 and 2. All right, pretty straightforward. And then finally, we're going to use all this stuff that we've learned about factors and zeros to kind of solve a random equation. So here's a polynomial that's missing some coefficients, right? We don't have a coefficient for x cubed or x squared. It's the same one apparently. And we're saying this is a factor, and that's the key. We're telling you that x plus 2 is a factor, which means the root is -2. More importantly and more specifically, when you plug in -2, you will get 0. Right? That's what a factor is. When you plug in the root, you get 0. So this is going to equal 0 when x is -2. So what we're saying is f of -2 equals -2 to the 4th minus some value k times -2 cubed plus some value k -2 squared plus 1. And that equals 0. And now you simplify. -2 to the 4th is 16. -2 cubed is -8, which makes this a plus 8k. -2 squared is 4. That's going to make it 4k plus 1 equals 0. Combine like terms, 8 plus 4, 16 plus 1. It's a very interesting answer, but it works. K is -17 over 12. So kind of an awkward fraction, but that's what makes it work. So all you're doing is using the fact that we know a factor is going to make it equal 0, and then just substituting, okay? So that covers everything we're going to talk about with the idea of real zeros. Next lesson we'll learn about the imaginary zeros, but you have most of the foundation for that already. So you should be good to do the next MathXL assignment.